Okay, so I was really when I started this study, I was really interested in when this rubble pylification happened, and I saw argon. I mean, it was mentioned in the talk before. It's sensitive to heat, and I thought that was really a good tool to answer such a question. So over the years, we analyzed several particles, and I think we got our story together, and I think it's pretty convincing. I'll leave it to you to see if you're convinced. Can I have the next slide, please? Yeah, so I want to start by very critical and important observation. So like Tomoki mentioned before, the particles are mostly highly equilibrated, with a few not equilibrated, but the one that we worked on were all highly equilibrated. So that means they come deep from inside the asteroid, the original parent asteroid, if you want. Next slide, please. So you've seen this graph before, probably it's from JAXA. And, if you look at the asteroid, it's obvious it comes from a huge shattering event. And my question was really to Tomoki in the chat, was really to ask if, it's possible that only part of this asteroid was shattered and we sample only the outside or the totality was shattered. I don't think the sample that tells us much about that, but yeah, I think Tomoki confirmed that it's possible it was much bigger than 20 kilometer. So anyway, when did that shattering happen and how? Next slide, please. So I'm using the argon-argon clock. So it's derived from the potassium-argon system, and it's very sensitive to heat. So if you heat the stuff above few hundred degrees, it reset. So that's important to keep in mind. Now, another thing that I want to mention, and really please keep that in mind, is that if it's equilibrated particle, it means it comes from inside the asteroid. Okay, so originally it was inside. Now 20 kilometer deep, maybe in the middle, maybe on the side, we don't know, but at least 20 kilometer deep. Deep inside means something very important. It means it was protected from surface impact, and if impact are so big that they reach this location, it should be indicated by some sort of shock. But it's usually 20 kilometers is pretty protected. Sorry. Next slide, please. Now, I mentioned you can reset the argon system with heat. Let's see how. The first heat that the particle, it's not a particle, it's inside rocks, inside the asteroid, but the first hit it would encounter is just the metamorphism at the very beginning of the history of the asteroid, inside the parent asteroid, so probably within a few million years. And that's the first uranium-lead date that my colleague showed before, the one at 4.6. But after that, the first opportunity for being reset is by excavation and hitting by a catastrophic impact. Because again, it's protected. And it's even more protected if you see no sign of shock in them. The second opportunity for resetting is because the heat is maintained in the newly formed rubble pile asteroid. So that means it cooled down slowly, and that means this cooling is going to be recorded instead of the initial shock. But those two, the first and second opportunity, happen in a very short time, and we'll see how long in this talk. The third opportunity is during normal standard impact on the rubble pile parent itself. And the interesting observation with impacting a rubble pile, it's porous, and impacting in porous material has a very interesting consequence. You don't need much shock to crank up the temperature and reset plagioclase for argon-argon dating. And that's something we discovered, recently with porous things. You can do experiment and see it's the case. People have done it to test things on impact crater on Earth, and you can do diffusion modeling, or you can do numerical modeling to simulate those temperature. So here is your 3 opportunity. But that means the first time you're going to see something, the oldest age you're going to see, which is not 4.5, that means the particle needs to have been either excavated at this time or already excavated. There's no way around that. You cannot reset those particles if it's deep inside the asteroid. And it's way, unless it's 4.5, everything at 4.4 perhaps, but 4.3, 4.2, 4.1, it's long time the asteroid has been cooled down, and it's not like the original heat anymore. So again, the oldest age we obtain is probably the slightly younger or the age of the shattering event. That's how I see it. And I scratched my head a lot around that, and I don't think there's any way around that. So that's important. Can I have the next slide, please? Now, in 2003, we published a study, and we had some interesting observation. So the age in red, they are in deep red, they are the one that are considered robust. They have nice plateau age. The one in pink, they are the one I'm not so impressed, including some of my own results, right? The oldest one on the far right, that's one of the first age we published with a huge error bar. So we sort of concluded things, but that was, that's just too large uncertainty. Slightly on the left, that's the uranium lead we talked just about. And the age we obtained in 2023, or a bit before that, that's the time of publication, were around 2.2, 2.3, sorry, let me start again, around 4.2, 4.1 billion. And I was really interested. And if you remember the rule that I mentioned before, that you cannot have age, that the oldest age you get is the age of the formation of the rubble pile, because you cannot reset argon before that. Then that means the age of the rubble pile formation is older than 4.2. Okay, and then if you go a bit on the left, you get the age at 2.1, the argon 1. It's a good age, but it's probably on the surface of the rubble pile itself. And then we get the isochrone that, I asked a question before because I said it covered the entire history of the solar system. That was a bit exaggerating, but you can see the error bar, it covers everything. That it's really, really hard to tell something about that. So this one I'm not a big fan. And then there was the pocket Al age, which is a mixture of grain, and we can see that they might have different ages. Each single grain have its own ages, so mixing grain together. Now you wouldn't do that on the detrital grain from mountain. For those people working on Earth, geologists, you would never ever do that. It's the same for here. We shouldn't do that. So that's what we conclude. Can I have the next slide, please? Yeah, so we conclude that, it must have been from the rubble pile structure, and we can have a bit of semantic. Do we call it Itokawa? Was that a proto-Itokawa? When do we start calling it Itokawa? That was certainly bigger than the present size of Itokawa, but the rubble pile structure must have formed before 4.2 billion. So it's older than 4.2 billion. So that's why we conclude it's been around for a long time. So, rubble pile lasts forever, at least Itokawa, because we get the age. And the reason for that we mentioned is because, they are porous. So if you hit a porous target, it just absorbs shock. That's what it does. It's like a cushion. So it's a space cushion, if you. Now we did some more studies after that. We get some more results. Can I have the next slide, please? And we analyzed 3 new particles. And I'm going to go through the results here. We just submitted the paper about that to GCA. We'll see where it goes, but I presented that a year ago at the Hayabusa Symposium. Next slide, please. So the first particle, and I want to attract your attention. I don't have a pointer, do I? No, I don't. So the first, the petrographic image, one of them is EBSD, the one in the middle. And if you know how to read EBSD, you can see that it's very homogeneous. And if it's very homogeneous, as far as EBSD is concerned, that means there's very little shock recorded in this particle. All right. Otherwise, it would have a range of color, like a rainbow, if you want, but it doesn't show that. So there's no sign of shock deformation.
10 minutes.
Yep, thank you. But we still see, despite that, some plagioclase structure. So that's the stuff in between that show almost no color, because it's glass. So it's not very good for indexing deformation. Now there's a zoom on one of these sort of vein. So it's sort of recrystallized melt with exsolution of K-rich area. So it's sort of plagioclase, if you want, but it really indicates some sort of melt, and yet no shock deformation in this one. And the age is 4130 plus minus 33. So, fairly precise, pretty good. That's 2 sigma. But again, it's similar to the age we obtained before at 4.2. So now it starts to be a cluster of age around this time period. Can I have the next slide, please? Now, the second one was super surprising. So there's a tiny bit of plagioclase. If you look at the element map and the phase map on the very top left, but the data really tell me there's a much bigger amount of plagioclase below the olivine. Okay, the olivine masks some more plagioclase because we had a decent signal on it. Now, that being said, the age is very interesting, is very surprising. It's, plagioclase, again, plagioclase for argon-argon is super sensitive to heat. So if you heat it above 250, 300 degree, it reset. So that means it was not heated above 300 degree, okay? Because it showed the age at the beginning of the solar system, a bit like the uranium-lead apatite age, 4557. So that's pretty interesting. It's really dating something that happened on the parent body and not the rubble pile this time. Now, if you look on the age spectrum, I didn't show you how to interpret that, but that's okay. The big, the big arrow show the amount of gas included in the age, so 4557. But a bit on the left, it shows in that there's some more recent event that happened to it. And it's not really an age, but it's sort of a semi-quantitative number that suggests something happened around 4115. Now, bigger about, but again, around this 41, 42, and 4.1, 4.2 billion years old age. So that's some support for that. Can I have the next slide, please? There's some other age, like we had well, not an age, but a near age that shows an impact which is probably younger than 700, but that's not surprising, that expected. But overall, we get now 3 age around 41, 42, this age around 2.3, and the age at 4.55. So now, next slide, please. What can we make of that? Now, I re-updated my graph and I included those age in there. So we get nothing new on the young side, but we start to have a cluster of age here. Okay, and if you get a big event, you expect to have many samples that recorded this age. And we also have an age here that is, similar kind of story as the uranium-lead age on its right. I wish I had a pointer. I'm using my mouse, but I'm just showing it to myself. So that's okay. You can guess what I'm talking about. especially since we're going to zoom on the next slide, please. How much time do I have left? Yeah, 5 minutes or so. So first stage I want to talk about is this 45, or I didn't update it, 57. So that's the metamorphic age. That's what happened on the parent body, and that's the cooling. Now, no surprise here. You know, if you get a parent body, it's going to cool in few million. And Tomoki showed at the end, he managed to show his animation, and that's very quick to cool down to almost zero by in 10 million years. So it doesn't bring anything to that story, but what it brings is like it was not affected by the shattering of the parent body. And I think it's a very interesting information. That means it was not subjected to temperature above 300 degrees. So that means, you know, when you break up a giant asteroid or 20-kilometer kind of giant asteroid, some of the part of the asteroid, they don't see much an increase of temperature. It's really a very heterogeneous process. Now, at the site of the impact, for sure, you're going to increase the temperature, but elsewhere and at the opposite, probably not much. So you're going to keep the history of the parent asteroid even accessible with the argon-argon system. Next slide. This one, don't worry too much about those graphs. They are not that necessary to understand the story, but now we get the age that are around 4.2, 4.1. Now, if they would overlap, I would have calculated a nice wide and mean age and say, wow, that's nice. That's the age of the breakup, but they don't overlap. Okay, and that's important to acknowledge. If they don't overlap, that means they don't tell the same story. What story do they tell? I think like based on some modeling that people have done and some analysis on different asteroid and modeling on cooling within rubble pile asteroid, it's very likely that in fact, this 40 million years difference is the recording of the cooling winds within the rubble pile asteroid right after the breakup. So in this story, you would have the breakup around 4.2, maybe slightly bit older. That doesn't mean to be honest, it's only 3 age. How do we know this is the absolute oldest? Maybe there's a bit older right here, but certainly it's probably very close to the one recording the formation age. And then you get a cooling of 40, 50 million years within the rubble pile itself. And I tested that if it's doable with a numerical model with argon diffusion. And yes, if you have a cooling like that, you can reproduce plateau ages without any problem. So I think this asteroid, the rubble pile, and a larger version of what we see now, formed initially at 4.2, not 1.5, and that it cools down within tens of million years, actually, within the rubble pile asteroid itself. Next slide, please. Now, that's the story I propose. Metamorphism. I had a figure like that in my PNS paper, but now I replace a few terms. That was about, symbol the tilde wave. Now I say at. So either we get excavation of part of the parent body or total disruption, reagglomeration. Parent body was much larger than that. The rubble pile parent body is probably 1 kilometer, 2 kilometers. I had no idea, but probably larger. And multiple collision trim it down. It lost material, and maybe it split into two. So do you still call one part Itokawa 1 and Itokawa 2? It's semantic. I don't care about that. I just care when the rubble pile structure was formed. And then over the year, many impact at the surface, 2.3 until the present day and its current shape. Can I have the last slide, please? And so that's the last slide. It was supposed to be an animation, but I suffered a PDF syndrome as well. So only the red age are correct on this one. And I conclude that, no, sorry. What I want to say is that now I told you a story. I told you the story when it formed. I told you the metamorphic things and how it was not affected some age were not affected by the disruption. Now I want to test my hypothesis. And what's better than data? Data, they are the best way to test hypothesis, I believe. So I predict that we would obtain something like that. A few age at 4.5, but not that many. Many more age around 4.1, 4.2. And then we have a gap here, and that's probably because Itokawa shed material into space. So everything that was at the surface impacted by impact on the rubble pile get lost and ejected by those impact. And gradually we start to have more data, and maybe I should have put more green bar here, as we go with the dating. And yeah, as a test, I have 5 more particles that I just sent to irradiation. At least there's that, and we'll see the result mid this year. That's it. I'm done.